Hello everyone. The title of this video is Graphing Rational Functions. Alright, so every example I'm going to be doing in this video is taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 5.6, called Rational Functions, and I'm under the heading Graphing Rational Functions. And each example I'm pulling from here is either going to be one of the examples from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Alright, so in the sketching of a rational function, you can read through a bunch of stuff here. They do have a little box here saying how to, given a rational function, a polynomial over a polynomial, sketch a graph. Alright, so you can go through all these steps here, which are fine. There's nothing wrong with these. I'm just going to go about it a little differently. It'll be basically the same order, but just bear with me. Alright, I'm going to be following the same. I'll write out the steps I'm performing, obviously, in this paper. Alright, so in order to sketch a graph of a rational function, you should be able to find intercepts, right? And that's for any function. You should be able to find x-intercepts, y-intercepts if it has any. You should be able to identify the vertical asymptotes or those removable discontinuities, which I put out a video on prior to this from this same section of this text. You also should be able to identify any horizontal asymptote or slant asymptote that the function may have. And that should really be enough. So over here, I'm going to put the steps that I usually like to follow when I make a quick sketch of a rational function. So first, if you can, I'm going to factor the numerator and denominator completely, if they're even factorable, which for this first example they're not. I mean, over the integers, x minus 5 in the numerator, 3x minus 1 in the denominator, they're both already linear. Then I'm going to state the domain just so I know what's allowed to be plugged in. Right? The domain of this function is basically any value except 1/3. Right? X can't be 1/3 because that would make the denominator 0. Then I identify any vertical asymptotes or removable discontinuities, and again I'm assuming you know how to do this from a previous video. Now remember, these removable discontinuities are just holes in the graph, but this particular one, since the fraction doesn't simplify any further, there won't be any holes in the graph. They're just going to be a vertical asymptote. So I see here, the fraction's already simplified. This is going to have a vertical asymptote at x equals 1/3. Alright, then identify any horizontal or slant asymptotes, which is also something I put a previous video out of on that topic. Identify the horizontal or slant asymptote. Well, here, again, I hope you remember all the rules. I'm assuming you've seen my previous videos. I'm going to make that assumption, and that you've read this, section 5.6 of this text up to now. These polynomials have the same degree, and remember the end behavior, the graph of a function, a rational function, is going to approach the graph of y equals the quotient on the ends. Now the quotient, when the degrees are the same, it's just the ratio of the lead coefficients. So this will have a horizontal asymptote. The line y equals 1 over 3, the ratio of the lead coefficients. So y equals 1/3. Okay, now you could also try to figure out where the graph of your function crosses the horizontal asymptote, because that can happen. Horizontal asymptotes or slant asymptotes can be crossed, but I'm not going to do all that. All right, and then we'll find the intercepts. X-intercepts, Y-intercepts. So for X-intercept, remember I'm putting in 0 for the output. So the only time a fraction is equal to 0 is when the numerator is 0. So that's 5, 0 here. If x were 5, the output would be 0. And that's the only one. That's the only value that makes the numerator 0. But not the denominator, though. Just make sure it doesn't make the denominator 0, which is fine. 5 is fine because it's not 1/3. And then for the y-intercept, you plug in 0 for x, right? If you can, if it's actually part of the domain, which it is here. And if I plug in 0 for x, the numerator is -5, the denominator is -1. -5 divided by -1 is +5. So 0, 5 is the y-intercept. All right, so I'll start sketching all this information on a piece of paper on a very rough graph. All right. So there's y-axis, x-axis, and the x-intercept 5, 0. All right, there's a point on the graph. 0, 5 should be on the graph as well. Y-intercept. Then these asymptotes, I'll put like little dashed lines. X equals 1/3. Right, so here's 1, and 1/3 would be like in here. I'll make a vertical dashed line like this. There's the vertical asymptote. The graph should be going to either infinity or -infinity on either side of that. And the horizontal asymptote's at y equals 1/3, which is, say here. I'll make a dashed line going horizontally at 1/3. And then after all this information's up, the intercepts, the asymptotes, if you need to, you can plot other points if needed. I'll say that's my last step. Plot other points if necessary, right, if needed. Because then after that, you should be able to use, and I guess sketch at the end. Right, fill the rest of it in. you should be able to use the asymptotes as a guide. Like this point up here, to the left of this vertical asymptote. I know the graph can't cross the x-axis again. The only x-intercept is at 0, 5. And I know that, y equals 1/3 is a horizontal asymptote. So I know the graph's going to be approaching that as you go to the left, approaching the horizontal asymptote. And it's got to either approach infinity or negative infinity on the left side of this vertical asymptote. Now, can you see why it can't go to negative infinity? Because it would have to cross the x-axis. But there's only one x-intercept. Right? I don't have an x-intercept over here, so it's got to go up to positive infinity on the left side of that vertical asymptote. And then same thing over here. I know the graph goes to the point 5, 0. It's got to go toward the horizontal asymptote as I move to the right, and toward the vertical asymptote, but this time go to negative infinity though. All right. Now it could have bounced off here and gone up, but that's where multiplicities come in. They do talk about the multiplicities of intercepts. X minus 5 is to the first power. So x equals 5 is a 0 with a multiplicity of 1. And you may recall, zeros with odd multiplicities, the graph crosses over the axis, right? So it's not going to bounce off and go back up, and it's not going to come down and then go back up again, because then there'd be another x-intercept. So it's got to cross over at 5 and then go to negative infinity. Right. Just using the asymptotes as guides. And again, if for some reason you want to plot other points, plug in other values, get other points, and do more stuff. But this is all I usually do. And then let's take a look. I'll go to that free online graphing calculator at desmos.com. And let's enter the function we were given and see how it looks to my rough sketch. Q of x equals x minus 5 divided by 3x minus 1. And you see there's the x-intercept 5, 0. See how the graph is crossing over because of that whole multiplicity of 1. Right? Here's the y-intercept 0, 5. And I can put up the asymptotes, y equals 1/3, x equals 1/3. Make them both the same color and maybe dash them in. Maybe I'll make them red and dashed. And you can see it looks exactly like my drawing. It's obviously better because it's a computer, but see how the graphs are approaching, the y equals 1/3 to the right. It's approaching y equals 1/3 to the left. Going to positive infinity on the left side of x equals 1/3. Going to negative infinity on the right side of x equals 1/3, right? Exactly like I had drawn. Right. So that just verifies that, my picture was a decent sketch. And you should probably double check your work after you're done anyway. Right, but yeah, so this is what I like doing. Right. Factor the numerator and denominator, state the domain, what's allowed to be plugged in, what's not. Identify vertical asymptotes, removable discontinuities, or where the holes are going to be. This will involve simplifying the fraction, right? Again, I put out a video on this earlier. Identify horizontal or slant asymptote. Again, I put out a video on this earlier as well. I'm assuming you know how to do all this stuff. Plot the intercepts, plot other points if necessary, and then, keeping in mind multiplicities, so you know how the graph should behave around x-intercepts. Make a rough sketch of the graph, right? Using the asymptotes and intercepts and other points as a guide. So let's do that again. And that's all I've got for the rest of the video, all my examples, doing the same stuff. Alright, now, here's a function called r of x equals 5 over x plus 1 squared. Alright, well, this is already factored, everything, denominator is x plus 1 times x plus 1. So the domain is easy to state. I can plug in anything I want for x except negative 1. And since this is already simplified, and there's still a factor of x plus 1 in the denominator, there's going to be a vertical asymptote. Now I'm just going to put VA for vertical asymptote at x equals negative 1. For the horizontal asymptote, the degree of the numerator is 0. The degree of the denominator is 2. And if you recall, when the degree of the denominator was larger, the x-axis was the horizontal asymptote. So I'm just going to put HA for horizontal asymptote. And that's y equals 0. And then for the intercepts, well, there's no x-intercept. The numerator is always 5. Right? The numerator is always 5, so there's no x-intercepts. You can't plug in anything for x and get an output of 0. Now for the y-intercept, if I plug in 0 for x, we're going to have 5 over 1. So the y-intercept is 0, 5. Okay, making a rough sketch over here. Again, x equals negative 1. There should be a vertical asymptote. There's no holes, no removable discontinuities, right? Just a vertical asymptote at x equals negative 1. The horizontal asymptote should be the x-axis. It's got the point 0, 5. Right. And I definitely should plot some other point, right? An easy one would be, how about negative 2? If x were negative 2, you'd have 5 over 1. You'd have negative 2, 5. Right? So here's another point that I felt I needed. I should be going around all the vertical asymptotes and intercepts. You should plot points around those if necessary. Then I feel like the graph's doing this. Over here, we're got to approach the horizontal asymptote as I go to the left, and it can't go to negative infinity to the left of the vertical asymptote because I need to be crossing the x-axis, right? It shouldn't have any x-intercept, so it should be approaching positive infinity to the left of that vertical asymptote. And the same thing over here. As I go from 0, 5, I go to the right, it should be approaching the horizontal asymptote, approaching the x-axis. And then as I go to the right here, it should be approaching infinity, because again, if it were approaching negative infinity, you'd have an x-intercept, but there are no x-intercepts. So the graph should look something like this. And again, let's just double check, let's verify with an actual graph, right? A nice computer-generated graph. So we were given r of x equals 5 divided by, and then x plus 1 squared. And look at that, right? It looks exactly like I had. I'll put in the asymptotes, y equals 0, right, which is the x-axis, and x equals negative 1. And I'll make those the same color and dashed. And you can very clearly see it looks exactly the same as I had. You have the point here is 5, 0, 5. Here's negative 2, 5, right, that other point I plotted. Going through those, and again, approaching the x-axis as you go to the far right and far left, approaching positive infinity on either side of x equals negative 1. Looks good. Looks like my drawing wasn't that bad. Great. Let's do that again. Alright, so this time we have a degree 2 divided by another degree 2. And yeah, I'm going to do the same stuff I've been talking about. First, let's factor the numerator and denominator. Now 2x squared plus 7x minus 15. That would factor to 2x minus 3 times x plus 5. plus 10x minus 3x, yeah. And then 3x squared minus 14x plus 15, that would have to factor this way. I need a is that even factorable? Oh yeah, that's factorable. Minus 3 here, minus 5 there. Right, because that'd be the plus 15, minus 5x, minus 9x, or minus 14x. Excellent. Alright, so numerator and denominator are factored. Now that the denominator is factored, I should easily be able to state the domain. It's all values of x except 5/3 and positive 3. Alright, so 1 and 2/3 and positive 3, right? Those aren't good. Those will make me divide by 0. And this is already as simplified as it gets, right? There's no common factor to cancel in the numerator and denominator, so these are where the vertical asymptotes are going to be. And there aren't going to be any removable discontinuities. There aren't going to be any holes in the graph. Just these asymptotes. X equals 5/3 is a vertical asymptote, but it'll also have a second one, x equals 3. Alright, and then they're the same degree. They're the same degree, so should have a horizontal asymptote. And that's y equals the ratio of the lead coefficients, which would be y equals 2/3. Okay. And as for the intercepts, this should have a couple x-intercepts. Again, whatever makes the numerator 0, but not the denominator. Right? So 3/2 and negative 5. So when x is 3/2, the output's 0. And when the x is negative 5, the output's 0 as well. And notice that both of those are to the first power. So both of these have a multiplicity of 1. I'll make that little note here. The multiplicity of 1 for both of them. Remember, that's an odd multiplicity. When there's an odd multiplicity, the graph will cross over the x-axis at those zeros. If there was an even multiplicity, right, if I had 2x minus 3 to the second power or something, then the graph bounces off the x-axis at the 0. Don't forget that stuff. Then for the y-intercept, if I plug in 0 for x, you'd have negative 15 divided by positive 15, that's negative 1. Alright, now there's also the thinking that the graph might cross the horizontal asymptote at some places. Now if you tried to figure that out, let me show you how you would figure that out, but first let me put all this stuff up. So again, vertical asymptotes at 5/3. There's 1, 2, 3. And 5/3, it's 1 and 2/3. So maybe around here. I'll put my vertical asymptotes in at 5/3 and positive 3. Deep. Alright, and then horizontal asymptote at y equals 2/3. Say here's 1, let's say 2/3 is there. Horizontal asymptote. Intercepts 1.5. Now 1 and 2/3 is bigger than 1.5, so there's like say 1.5 here. There's an x-intercept at 1.5 and at negative 5. Okay, so I definitely need some other points here, and then 0, -1. Okay. Alright, so now, remember I said earlier, there will be some scenarios where you think, hey, this thing probably is going to cross the horizontal asymptote or the slant asymptote. So how do you figure out where that happens? Well, unfortunately, sometimes you gotta perform a little division. Basically, where is this going to be equal to 2/3? Right. Now, if you actually perform the long division, so let's see if does the graph. This is something you might want to keep in the back of your mind. I know I said I wouldn't talk about it earlier, but I thought about it a little more. I was like, maybe I should. Does the graph cross the horizontal asymptote or slant asymptote? Well, here's how you do this, right? Divide. We have, now it's going to be long division here. We're taking 2x squared plus 7x minus 15 and dividing by 3x squared minus 14x. Now this will involve some fractions and stuff, but it should be doable. Remember, divide the lead terms as 2/3. Then multiply, you got 2x squared. And then minus 28/3 x. And then 3 goes into 15. 5 times that's 10 plus 10. Let's subtract all of that from the line above it. And the x squareds are gone. Now 7x minus -28/3, that'd be plus 28/3. Now 7 is 21/3 plus 28/3 would be 49/3 x. And then -15 minus 10, that's -25. And so what we have here is that g of x is equal to 2/3 plus, and then 49/3 x minus 25 divided by, the divisor, 3x squared minus 14x plus 15. And then the question is g of x ever equal to 2/3? And yes, when this is 0, right? When the remainder is 0, basically. And that happens when x equals 75/49. And if x were equal to 75/49, then the graph crosses the horizontal asymptote. Right? So that's a lot. You don't really have to do that every time, but 75/49 is 1 and 26/49. That's more than 1.5, so it's over here. So the graph is going to cross here the horizontal asymptote at 75/49. That's, I'm sorry about the tinyness of this. So the graph's going to now be doing this over here. It's going to be crossing -5, 0. Got to go toward the horizontal asymptote as I go to the left. Again, the multiplicity of -5 was 1, so it's crossing the x-axis. It's got to come down and hit the y-intercept at 0, -1, and then come up and hit 1.5 at 3, and with 3 halves has a multiplicity of 1 again, so it crosses over, and it's crossing the the horizontal asymptote here at 2/3 at 75/49. Again, if you didn't see that, you could still have probably figured that out, and then going up to infinity to the left side of that vertical asymptote. So the graph will look something like that to the left side of that asymptote. Now I just need to know what happens around these other asymptotes, so I definitely need to plot some other points. All right. So let's plot other points. Well, if I were to plug in, say, 2, right, because I know what happens to the left of 5/3, what about to the right of 5/3? If I plug in 2 for x, bear with me here. I'll go to the factored version. So g of 2 is going to be, 2 times 2 minus 3. That's 4 minus 3, that's 1. So 7 in the numerator, 2 plus 5. Then 6 minus 5 is 1. 2 minus negative 3 is negative 1. So it's negative 7 for the output when the input is 2 to negative 7. And that's really all I need to know what happens between these two asymptotes, because there aren't any x-intercepts, so it can't be flowing up and crossing the x-axis. All right. And we already know that there's only the one point where it crosses the horizontal asymptote as well. So the graph down here has got to be doing this, going to negative infinity here, coming up, hitting this point, maybe going up a little further, but then it's got to curl back down at some point, and then go to negative infinity over here as well. But curl almost like a parabola between these two asymptotes. But it can't go to positive infinity because it would have to cross the x-axis, and we know there's only these x-intercepts. And then how about to the right of 3? What happens over to, we know what happens to the left of that asymptote between these two asymptotes. What about to the right of x equals 3? Let's say I plug in 4. What's g of 4? Go to the factored form. 2 times 4 is 8, minus 3 is 5, times 9 would be 45 in the numerator. All right. And then 12 minus 5 is 7, 7 in the denominator. So 45 sevenths, that'd be 6 and 3/7, almost 6.5 for the output. 1, 2, 3, 4, 5, 6. Here's 7, and then we got 45 sevenths here. There's that point. And again, once you have a point in that area, you should be able to tell what's happening. It's got to approach the horizontal asymptote as you go to the right and approach the vertical asymptote, again, more smoothly than this, but approach infinity to the right of that vertical asymptote. All right, again, it can't go down because there are no more x-intercepts. We found all the x-intercepts. Okay, so that was a lot. All right, that one was kind of a pain because of the fact that it does cross the horizontal asymptote at some point. All right, but still manageable. All right, still doing kind of the same steps every time. What's factoring? What's the domain? What are the asymptotes or holes? What's the horizontal asymptote or slant asymptote? X-intercepts, Y-intercept. Plot other points if need be, and then understand, that the asymptotes are guides. The graph that you're drawing should be approaching these asymptotes in some fashion. All right, so let's take a look. Let's take a look at how this graph compares to the real thing. All right. Okay, so we were given g of x. We actually put it in there. Equals, the numerator is 2x squared plus 7x minus 15. Denominator 3x squared minus 14x plus 15. And then see, there's negative 5, 0. Here's 0, negative 1. Now it goes down a little further, so my drawing's a little off, but then it crosses at 1.50, the 1.5. And then if I put in the asymptotes, right, we had y equals 2/3 for the horizontal asymptote, x equals 5/3 for one of the vertical asymptotes, and x equals 3 for another one. And I'll dash all these in. Let's make them all red. And make them dashed. Okay. And you can see the graph approaches, positive infinity, goes up forever to the left of 5/3. And look at this point here. See, that's at 1.531, 2/3. 1.531 is the 75/49ths. All right, if I calculate over here 75/49ths, I found out 49ths. See the 1.5306, 1.531 when they round to 3 decimal places. That's the point where the graph intersects the horizontal asymptote. But yeah, and then look between See, there's 2, -7 down here. Well, actually not 2, -7, a little higher than that, but still, you see how this little almost a parabola shape between the asymptotes down here like I had? And then we had the 0.445, wherever that was, somewhere up here. And, approaching the horizontal asymptote to the right, approaching infinity to the right of the vertical asymptote here. Yeah, everything looks pretty good compared to what I had. My drawing isn't terrible. And that's the key though, you're just making a rough sketch. Alright, so if you're off a little bit, like this should be coming down a little more, this should be going up a little more. Like, I don't care about that. I'm making a rough sketch of this, just getting the general shape. Have the asymptotes in, have the intercepts, have some other points if need be, and use the intercepts and the asymptotes as a guide. And that's all I'm doing. Right? I know that was a complicated one, and they can be a little complicated sometimes, especially if the graph crosses the horizontal asymptote. But you can figure out where that happens. It's not that it takes a little bit more effort, but you can do it. All right. So next example. Got a b of x equals x squared minus x minus 6 divided by x squared minus 4. Once again, factor in the numerator will be x minus 3 times x plus 2. Factoring the denominator, x minus 2 times x plus 2. Now before I simplify, right, I know you see the common factor of x plus 2, I'm going to state the domain. Because the way they gave it to me, I can use any value of x I want except 2 and -2. Right, those are the values that can't be plugged in for x the way they gave me the function, right? The way it looks in the beginning. As if I plug in either of these two, the denominator is going to be 0. Now if you simplify, right, they both have this common factor of x plus 2, we get the following. X minus 3 in the numerator divided by x minus 2. So this time, because there was that cancellation, there's going to be a hole in the graph, one of those removable discontinuities. So there's a vertical asymptote at x equals 2, right? That x minus 2 is still in the denominator there. And there's going to be a hole in the graph at x equals -2. And if you want to figure out where that hole is, remember you plug -2 into the simplified version, and that'll tell you where that missing point's going to be. If I plug in -2, you got -5 in the numerator, -4 in the denominator, that'd be +5/4. And I'll actually, this is going to be an open point, a missing point. All right. So vertical asymptote at x equals 2, and a hole when x equals -2. All right, now for the horizontal asymptote, or the slant asymptote, well here it will be horizontal because again they have the same degree, so just the lead coefficients 1/1, you have y equals 1 will be the horizontal asymptote. Then for the intercepts, if it has any, the numerator is going to be 0 when x equals 3. Now I know it would be 0 when x is -2 as well, but remember x can't be -2. I want something that makes the numerator 0 but not the denominator. So -3, 0, this is the only x-intercept. Or sorry, not -3, +3, right? That's x minus 3. +3 would make it 0. So +3, 0. And once again, I'm noticing, x minus 3 has a power of 1. So this is a multiplicity of 1. The graph's going to cross the x-axis. I'll write that here, cross x-axis at this because the multiplicity is odd. And then the y-intercept would be 0, 3/2. All right, be -6 divided by -4, +3/2. And this should be enough. Now, if you want to determine, does it cross, let's see, does it cross the horizontal asymptote? Let's divide. All right. And you know what? I'll just do it here. So does it cross the horizontal asymptote? All right. Well, if you divide these, you get 1, and times that would be x squared minus 4. And then that's gone. Then you have negative x, and then negative 6 minus negative 4, negative 2. And then, yeah, so the function here is equal to 1 plus negative x minus 2 over x squared minus 4. So when x is negative 2, but x can't be negative 2, so, is b of x ever equal to 1? No. All right, because again, if this simplified, when x, this is equal to 1, if you pull out a negative 1, x plus 2, x plus 2. Well, actually, say this is x minus 2 minus 1. Yeah, then minus 1 over x minus 2 if you simplify completely. And notice this term here will never be 0, so no. All right, so we're fortunate here. The graph of this will not cross the horizontal asymptote. All right, now I have, I think, pretty much everything I need. I might have to plot some other points, but we'll see. So y-axis, x-axis, x equals 2, y equals 1 are the asymptotes. And it's going to have a hole at negative 2 and then 5/4. Now 5/4 is 1 1/4. So there's going to be an open point right here. The graph is going to approach that point on both sides, but then have that one missing point. So I got a hole there. And the intercepts, you got 3, 0, and 0, 1.5. All right, and that should be enough. Graph should be doing this. Using the asymptotes as a guide. Approaches the horizontal asymptote on both ends. It's got to approach infinity on this side of that asymptote, negative infinity on this side of that asymptote. It's got to cross over at x equals 3. That's why I said, right, crosses the x-axis because the multiplicity was 1. So it should have this rough look to it. Let's see. Again, I like to verify my answers, make sure things look good. And I just got a couple more examples after this, so hopefully you're bearing with me here. So we were given b of x equals, numerator had x squared minus x minus 6, denominator has x squared minus 4. And yeah, that looks exactly like I drew, right? There's 0, 1.5, there's 3, 0. And it's going to have a hole at negative 2, 5/4. There should be a hole here. Yeah, see that open point, negative 2 undefined, and you see how it's at about 1 1/4. If you put the point negative 2 comma 5/4 in there, it would fill this hole. And y equals 1 is horizontal asymptote, x equals 2 vertical asymptote. Everything looks great. Everything looks wonderful. All right. Good. So let's keep that up. Right, so like I said, just a couple more of these. So here's another one. Now this time the numerator has a degree that's higher than the denominator, so it'll have a, it's only 1 higher too, so the quotient's going to be a degree 1. This is going to have a slant asymptote, right? Not a horizontal asymptote. Okay. Now if you factor the numerator, pretty sure we can. Yeah. 2x in one, x in the other. You can do the grouping method if you wish. Let's see, negative 40. So I need negative 8, positive 5. So negative 4 over here, positive 5 here. 2x plus 5 times x minus 4 would be 2x squared minus 3x minus 20. And then the denominator is still just the factor x minus 5. Alright, so the domain's easy. I can plug in anything for x I wish except 5. And this doesn't simplify any further, so that's going to be where the vertical asymptote is at x equals 5. There will be a vertical asymptote. Now for the slant asymptote, I have to actually divide. Now you can do synthetic division here too, because it's a linear with a lead coefficient of 1. But I'm just in the habit right now of doing long division. So for the slant asymptote, divide these. You got 2x and multiply. It's 2x squared minus 10x. Subtract all that. Negative 3x minus negative 10 would be negative 3 plus 10x. That'd be positive 7x, and then drop the negative 20, and then 7x divided by x is positive 7. And you got 7x minus 35, and then subtract all that, and your remainder is 15. Alright, so you could also write this as 2x plus 7 plus 15 over x minus 5. You could write it this way as well, right? The k of x. And since the remainder is always going to be 15, the graph of k will never cross the slant asymptote, so that's nice. But the slant asymptote is y equals the quotient, y equals 2x plus 7. And then for the intercepts, you got what makes the numerator 0 but not the denominator. For the x-intercepts, that'd be negative 5 halves, comma 0, and positive 4, comma 0. And again, at both of these, the graph is going to cross the x-axis. We haven't seen anything yet. We will in the next example, but where the multiplicity has been even. So far we have 2x plus 5 to the first, x minus 4 to the first, odd multiplicities. So the graph should cross the x-axis at these intercepts. And then the y-intercept would be 0, 4. Right, negative 20 divided by negative 5. Alright, let's take a look. Alright, so I'll make a rough sketch over here. Pretty tiny. Yeah, so we have x equals 5. Should be the vertical asymptote. And then y equals 2x plus 7 is the slant asymptote. Now you know what that looks like, right? You have 0, 7, 1, 9 on that line. Right? And it's a line with a slope of 2 and a y-intercept of 7. Right? So something like this. Maybe I should have given myself a little more room here. But here's the slant asymptote and the vertical asymptote. Okay. Now, some of the points, negative 2.5. Now this would cross at negative 7 halves. It's negative 3.5, so negative 2.5 is over here somewhere, right? And then 4, 0, 4, 0, and 0, 4, which would be under this. So this part of the graph is easy enough, right? The graph should be again going through all these 3 points, but approaching this line as you go to the far left, coming up and then coming down through here, approaching negative infinity that way, right? It should look something like that between those. But what about up here, where my finger's pointing? So I need to plot some other points. How about like 6? When x equals 6 to the right, to the right of the, we know what to the left of the vertical asymptote looks like. How about to the right? So what's k of 6? Well, if I look at the factored form, that'll be easy. Well, actually, here that'll be easy too. It doesn't matter. Alright, so we have 12 plus 5 is 17, times 2 is 34, divided by 1, 34. 6, 34. Now that's going to be, now these will meet This is the point 517. So 634 is definitely going to be up here somewhere. Here's 634. And the graph's got to be some sort of curl like this then. It's got to approach the vertical asymptote, approach infinity to the right of the vertical asymptote, and approach that slant asymptote as it goes to the far right. Again, just a very, very, very rough sketch. And let's see. Let's compare it to the real thing. K of x equals, numerator 2x squared minus 3x minus 20, denominator x minus 5. And if I zoom out big enough to 34 up there, right there it is. And I'll put in the slant asymptote that we had, y equals 2x plus 7. And you see how it's following that line to the far right and the far left. I can make it a dashed line, but we see it, hopefully you see it. And x equals 5 is a vertical asymptote. It's got all the points I mentioned on it. You could look at a table, but I'm satisfied. All right, I'm happy with the way my graph looked compared to this one. All right, I've got one final example. All right, so this one, everything's factored already, which is nice. Numerator is x plus 2 squared times x minus 5. Denominator is x minus 3x plus 1x plus 4. So no common factors in the numerator and denominator. I'm not going to cancel anything. So I can tell you what the vertical asymptotes are going to be right now. I know the domain is everything but 3, -1, and -4. Right? So that's where the vertical asymptotes are going to be. X equals 3, x equals -1 will be a vertical asymptote, and x equals -4 as well. Right? Because those make the denominator 0, but not the numerator. Now, up top, the leading term is going to be x cubed. It's going to be x cubed plus something. Same thing with the bottom. If you multiply all the lead terms of the factors, it's going to be x cubed plus something. So it's a degree 3 divided by a degree 3. Same degree, so the horizontal asymptote is going to be y equals, the ratio of the lead coefficients should just be 1 over 1, y equals 1. Now, again, it would be a big pain to figure out if y equals 1 is crossed by this, so I'm not going to do it this time. But if you want to multiply these out and then divide them and see if it crosses y equals 1, be my guest, but I don't think it will. Now the intercepts. You have -2, 0, and 5, 0. Right, if you plug in -2 for x and 5 for x, the numerator is 0, but the denominator is not. All right, now here's one where you see x plus 2 is squared. So this intercept of -2 has a multiplicity of 2. The graph's going to bounce off the x-axis here. Right, it has an even multiplicity. Whereas 5, 0, x minus 5 is only the first power. It's odd. So the graph's going to cross over the x-axis at 5, 0. Right, hopefully you remember all that multiplicity junk from polynomials. And then if I plug in 0 for x, now this one I have to actually kind of calculate here. If I plug in 0, let's just do it here. Z of 0 will be 4 times -5 in the numerator, and then -3 times 1 times 4. So 4's cancel at positive 5/3. So 0, 5/3 for the y-intercept. All right, and that should be enough information. Maybe I'll have to plot some other points. We'll see. So 1, 2, 3, -1, 2, 3, 4. There's -4. There's -1. There's positive 3. Those are where the vertical asymptotes will be. Y equals 1, horizontal asymptote. Intercepts -2, 0, 5, 0. And 0, 5/3, so 0, 1 and a third, 1 and 2/3, so it's up here somewhere. Right, there's 0, 5/3 above 1. Alright, and I will need to plot some points. So how about over here? Because I know I have a point between these two asymptotes, I have a point between these two, I have a point to the right of that one. I just need a point over here. So how about when x is -5? Right, so let's see, what's z of -5? That would be -5 plus 2 is -3 squared is 9 times -10 in the numerator, and then -8 times -4 times -1 in the denominator when x is -5. Alright, so this is 2 goes into that twice, that 5 times, so that's it, 45. These are negative over negative, negative. This is a positive 45/16, which is, between 2 and 3. So between 2 and 3, so somewhere up here. Alright, something above 1. Alright, so -5 and then, positive 45/16. So, and that should be enough, really, to graph this. So we got something like this, with those asymptotes as guides, in between here and here. Now I know at -2, 0, the graph's going to bounce off. And another thing about multiplicities, which again, hopefully you've read the section. See, you can even use multiplicities for the denominator zeros. -4 is a vertical asymptote. X plus 4 is the first power. So it's going to be going to opposite directions. If it's even, they go in the same direction on both sides of the asymptote. If it's odd, they go in opposite directions. But again, that's something you can read on your own. I just happen to know that. And then you're going to come up here, bounce off here, come back down. Got to be something like that between those two asymptotes. And then here, again, it can't be going to negative infinity because there are no intercepts in here, so it's got to be doing something like this between these two asymptotes. Again, exactly how low things go, I don't know, but I know it can't cross the x-axis in here. It can't touch the x-axis in here somewhere, and there's a point up here, so it's got to be going to infinity on both sides. And then for 5 over here, you're going to be doing something like this, and approaching the horizontal asymptote to go to the right. So again, very, very rough sketch. And let's see how this stacks up to the actual thing. So we were given z of x equals, the quantity x plus 2 squared times x minus 5 divided by x minus 3 times x plus 1 times x plus 4. Alright, yeah, that looks pretty similar to what I had. And if I put the asymptotes up, but -4 is a vertical asymptote, -1, positive 3, y equals 1 is a horizontal asymptote. This looks pretty similar to what I had. See at -2, 0, it bounces off the axis. At 5, 0, it crosses over. Just like I had in my drawing. So this looks pretty good. This looks pretty good compared to my drawing there. If you kind of bounce back and forth, see. All right. Okay. And again, if you didn't know that thing about multiplicities in the denominator, just plug in other points. Plug in -3 and see what happens. It should be below the x-axis, and if that was below the x-axis, then the whole thing's got to be, right? Because it's going to bounce off -2, 0. So that you can get a lot of information just by plotting other points, right? So again, the steps I was following. You factor the numerator and denominator, state the domain, identify vertical asymptotes or holes in the graph, removable discontinuities, identify horizontal asymptote or slant asymptote. You may want to ask yourself if the horizontal asymptote or slant asymptote gets crossed at all, but that might take a bit. what are the intercepts, and then use all that information, and maybe you'll have to plot some other points around these asymptotes. And once you've got all that information down, plotted some other points, you should be able to make a pretty decent rough sketch of the graph using the points you plotted and the intercepts and the asymptotes as guides. Great. Alright, and I'm hoping that watching me do these 6 examples here helps you in some way when you're asked to graph a rational function on your own. And thank you very much for watching.